Thank you. Welcome, welcome everyone. As you guys are signing up, please, find a seat so we can get. All right. All right, so we get started. It's a pleasure to introduce a very good friend and a colleague of mine, Professor Andrea Alu. Professor Andrea Alu is a full professor and a Temple Foundation endowed professor at the University of Texas at Austin. Professor Alu got his undergraduate and graduate degrees from University of Rome, from Rome, Italy. In 2007, he defended his PhD and did a one-year postdoc at the University of Pennsylvania, where we spent some time together. And in 2009, he joined the faculty of University of Texas in Austin, and very shortly after that, he became a full professor a couple of years down the road. His current research interests span a large area, including metamaterials, plasmonics, electromagnetics, optics, photonics, scattering, cloaking, and a lot of other areas within the electromagnetics community. Andrea is a very prolific author. He's published close to 400 journal papers as a faculty and as a student, and his work has been recognized by a lot of prestigious awards, including the NSF Alan T. Water Award in 2015, the Edith and Peter O'Donnell Award in Engineering, the ICO Prize in Optics, the OSA Adolph Lomb Medal in 2013, the Ursi Isaac Koga Gold Medal, and many, many other prestigious awards. He's also a recipient of the NSF Career Award, the Air Force, and the DTR Young Investigator Award. He also has a keen interest in commercializing his technology. He's the CTO of a company called Silicon Audio RF Circulator, where he's commercializing a couple of the technology that he invented in his lab, the magnetic-free circulator for audio and radio waves, and we'll hear about some of that work today. So please join me in welcoming Professor Alu.
Okay, thank you, Victor, for inviting me. It's a great honor to be here visiting many friends, Victor and many other colleagues in this top school, and I'm happy to give you an overview of what we've been doing in the broad area of metamaterials with interests from radio frequencies to optics and acoustics. I want to give credit to my group members that contributed directly to some of the research I show next, and also these alumni that actually did a lot of work in this area when they were in my group, and they're continuing. So since this let me see, got stuck. So since this talk is kind of broad, I want to first introduce what a metamaterial is. Right? These are pictures showing optical metamaterials. What you see here are nanostructures in the range of 100 nanometers in length, with periods. These are kind of periodic structures in the order of 150 to 200 nanometers. And as you see, they are designed and arranged properly in a lattice, controlling not just the composition of the materials, like in a regular mixture, but also the orientation, the alignment, the geometry, the material composition, the background. And all these knobs, these degrees of freedom, allows us to build an artificial material that is homogenizable, can be described as a bulk material with properties that go beyond what nature offers us at this range of frequencies. So the idea is to mix gold and glass, or silver and glass, but yet get a response very different from both gold and silver and glass, or an average of them. And that is enabled indeed by controlling locally the orientation and the geometry and the design of these structures at a deeply subwavelength scale, so that you can still treat the material as a homogeneous structure. This has opened a lot of interesting directions in the last 15, 20 years. This is an example of a recent exciting work in the area of optics, in which people have shown that you can actually manipulate these inhomogeneities on a surface to imprint on an optical wavefront some desired shapes. Essentially, you can generalize the way in which light emerges from an interface by imprinting on the interface specific gradients of impedance on the surface. These are called metasurfaces and are appealing because it's easy to print large areas in which you control locally at deeply subwavelength scales the profile of the emerging beam. What's important is that these structures are deeply subwavelength, so they require strong light-matter interactions. A regular material doesn't really interact much with light over a scale that is 100 nanometers, and that's why we use typically metallic structures that have plasmonic resonances. They have interface resonances between the surface of the metal and air, and that strong resonance can enable large light-matter interactions at deeply subwavelength scales. Some of the holy grails of metamaterials, how this topic got started and excited many researchers. This is an example of a material in which the permittivity and permeability is negative compared to the free space. And what you can prove through Maxwell's equations is that if you shine light through this material at the interface, the light bends the opposite way. And one of the ideas was, can we create a planar lens that can focus from this point to that point, independent of the position? So you can create an aberration-free lens that also has sub-wavelength resolution, can beat the resolution of a conventional lens. Another interesting opportunity is if we can manipulate the way in which light travels in materials, can we bend it in a way that it avoids a region of space and create what is known as a cloak, a structure that can hide a certain volume from an impinging wave, and yet the structure looks transparent, looks invisible to the outside observer. These have been exciting the community and beyond, but also have failed really to deliver products so far. And some of the reasons for which there is this slow transition into practical devices that actually work better than what we have available today are listed here. For instance, typically these metamaterials are passive, and since we want to enhance light-matter interactions at deeply subwavelength scales, you get problems with loss and with other issues actually related to bandwidth that come out from passivity. They are also time invariant, so you can create interesting structures, but then you are stuck with that functionality that may not be ideal for devices. Since electromagnetic phenomena tend to be mostly linear in most materials, when the structures are thin and small, they tend to have very weak nonlinearities. Typically, when we want to have large nonlinearities, we engage wave phenomena over long distances, and this is not the case in metamaterials. So these functionalities are limited to linear problems, and they're fundamentally limited by symmetry constraints. If I have a very thin metasurface, then geometrically this is bound to respond symmetrically on the two sides. And also there are more fundamental symmetry constraints I will discuss during my talk that are related to time reversal symmetry. So my group has been interested in exploring ways to overcome some of these constraints by exploring hybrid phenomena in which we combine multiphysics operations on the same subwavelength platform. An example is optomechanical interactions. I will show you a couple of these examples. And time-varying or time-modulated structures that overcome some of the constraints I discussed before, or materials with gain and active systems that can enable overcome some of the passivity constraints that I was discussing. I will show you a few examples during these next 50 minutes or so. So the first example is these hybrid metasurfaces in which we have considered combining the concept of a metasurface with a very interesting material platform that is well established in the condensed matter semiconductor community, that is multi-quantum wells. These are engineered systems at the level of few nanometers in scale, in layers, in which by controlling the different composition of these layers, you can actually control the band diagram of these materials. And in particular, you can introduce or engage inter-subband transitions between different bands, and they are associated with very strong nonlinearities. In fact, levels of nonlinearity, this is chi2, the second order nonlinearity in optics, that is orders of magnitude larger than what a regular optical crystal can provide. So the question is, can we use this as a platform to build new metamaterials that engage this quantum phenomena and couple them with strong electromagnetic resonances? One caveat is that these materials have these inter-subband transitions respond to electric fields polarized vertical to the layers. These typically are thin layers, so when you come in from free space, you don't couple much energy to this polarization, if they are especially on a ground plane. So the idea is, can we use surfaces like these that are patterned on the top with nano antennas that engage specific resonances that first convert transverse fields into vertical fields. They engage the nonlinearities in the multi-quantum well, and then they engage other nonlinearities at second harmonic, for instance, exploiting this transition at the, related to the second order nonlinearity, and radiate out efficiently into the far field. To do that, you need to design proper nanoantennas that not only enhance the fields due to plasmonic resonances, but also convert polarizations properly and overlap the two modes in a way that is constructive in phase. You can do that. This is an example of a realization at, with a surface that is 400 nanometer thick, and yet it provides very large nonlinear second harmonic generation given the amount of material that we use for these structures. The effective susceptibility, nonlinear susceptibility of these surfaces is giant, is orders of magnitude larger than any natural condensed matter system. And the key is indeed to enhance this overlap integral between the fields induced at each pixel. What's interesting is that compared to a regular crystal in which you build up nonlinearity by letting propagation travel into the material, here this happens locally. So you don't have to worry about phase matching, about constructive interference of this build-up of second harmonic generation as the wave travels, and you can control it at the nanoscale, at the deeply subwavelength scale, how the second harmonic or this chi2 response emerges. And these are more recent results in which we etched the structure of the material to engage more the modes close to the nanoantennas, and that enables a larger overlap integral that translates into even larger chi2 second harmonic phenomena. And there is a path to get a few percent conversion efficiency in these structures, again at the deeply subwavelength scale, such that you can take this surface and control locally the nonlinear response. So do something like what I was showing you for the patterned surface in the linear regime, but now with nonlinear optics. So I send in a beam here, I convert it to a different frequency, or I do phase conjugation, or mixing, harmonic generation, but I can do it locally, pixel by pixel at subwavelength scale. As an example of this, this is a concept related to the Berry phase. Essentially, the idea is that I have a surface, again, very thin compared to the fundamental frequency. I illuminate it at frequency omega, and I look at the reflection at frequency 2 omega. And the idea is that these pixels are designed, on one hand, to get very strong overlap integral, so very large nonlinearity locally, but also if I excite it with circular polarization, when I rotate this pixel, the only thing I change is not the amplitude of the nonlinear generation, but the phase, the relative phase, because rotating it is as if the surface gets closer or further away from the circularly polarized wave. That way I can control locally with subwavelength resolution the phase of the nonlinear generated beam. So if I introduce a gradient, like what I showed you before for the linear case, I get a pattern, an imprint of the nonlinear beam at the output that follows the same gradient. In fact, you can write it formally. This is actually the radiating currents at 2 omega in the substrate that are induced by the impinging wave, and you see that the amplitude to first approximation is constant. It's not affected by the rotation, but the rotation of the geometrical rotation of these pixels corresponds in a control of the phase, pixel by pixel, over the surface. So you can imprint an arbitrary phase pattern on the surface by rotating properly the inclusions. And when you come in for opposite circular polarization, you get the opposite phase. So you can actually get a twofold response from the same surface by changing the impinging excitation of the beam and control all these output beams at, with arbitrary choice. This is an example of an experiment in collaboration with Misha Belkin in my department. We were showing that by introducing these linear gradients of rotation, you can indeed get an emerging beam. So you illuminate the surface is always a normal incidence with a constant phase at frequency omega, but the emerging beam has a different angle of radiation that depends on the gradient with which you rotate these pixels in the structure. And you can do different things. You can do lensing, focusing, defocusing. In fact, as a function of how you excite the structure, you will get a different output in the nonlinear optics. This is one example of how a hybrid metasurface can provide interesting opportunities beyond what is conventionally achievable with natural materials. But even more fundamentally, I was discussing the issues of symmetry that comes up when you build a metasurface. So this is a conventional linear metasurface in which I have the same gradient of impedance that takes an impinging wave and bends it by exploiting the gradient. There are some inherent symmetry constraints that come from the fact that this surface is actually very thin. First of all, when I excite it from one side, I get a similar response on both sides because of geometrical symmetry that I can break by making it thicker. But the other big constraint that actually boils down to time reversal symmetry of Maxwell's equations is that when I excite the structure from the opposite side, I have to get the same response. So if I excite from here and I measure transmission in this direction, it is a certain amount. When I excite from that side, I get the same transmission here. This symmetry is always there and comes from the reversibility of Maxwell's equations in time. However, it's not always a good thing. I mean, we count on it when we transmit and receive signals, the symmetry in which signals travel in the two directions. But there are examples of technology in which we want to avoid that symmetry. Right? A typical example is an isolator, when we want to be able to transmit a signal down a certain path, but we don't want to receive it back, any reflection or any, we don't want interference or even damaging of the source by reflections. Duplexers and circulators are a generalization of isolators. These are structures that allow you to transmit a signal through a certain path, but the signal received actually goes somewhere else. Again, you need to break the symmetry in which waves travel in a material. And to do that, you need a non-reciprocal device. You need to break that symmetry. This is very useful for full duplex communications or for radar systems, because you want to be able to transmit and receive through the same antenna. That would be holy grail to have it in a cell phone or in a handset device, because it would allow us to transmit and receive signals on the same frequency channel through the same antenna at the same time. We cannot do it today, and in fact, this implies that we have to occupy two different channels when we make a phone call, one to transmit our signal and one to receive it, and that limits the spectrum available for other users. So the reason why these systems are not today in a handheld device or in a cell phone is that the typical way in which we break reciprocity is using magnetic bias, magnetized materials. And this boils down to Lorentz reciprocity theorem. This is a general theorem that tells you that if I exchange source and observer, I get the same response. To break this equality, you can work with breaking one of the fundamental assumptions, hypotheses, that from which you derive this one from Maxwell's equations. The first hypothesis is that the materials are symmetric, have a symmetric, a time reversal symmetric response. This is written here in terms of tensors. The second one is the time invariance of these materials, and the third one is the linearity of the material themselves. So as I was mentioning, the common way of breaking reciprocity and building isolators and circulators is to apply a magnetic bias. That breaks the symmetry of the material when a wave travels in the parallel or anti-parallel to the magnetic bias. It feels a different material, and therefore I can build an isolator based on interference between different paths, or a circulator. But these magnets are very difficult to integrate on chip. You can't put a magnet directly in a cell phone because magneto-optic effects are weak. And especially when you push it to higher frequencies, this becomes very large devices compared to the wavelength. So can we realize an isolator without magnets? One way that actually has a long history of explorations since the 50s and 60s is to look at time variant materials, so breaking time invariance. And recently there has been a lot of work in this area showing that you can use mechanical motion or spatiotemporal modulation schemes to actually isolate or circulate, or break reciprocity in an integrated device. The way we came into the problem was actually inspired by the way in which magnetized materials work. If I take a magnetic material and I apply a magnetic bias, I see that I create what is known as a Zeeman splitting. Basically, in absence of magnetic bias, the molecules have this degeneracy in energy levels for a right-handed or left-handed state. But when you apply a magnetic bias, you split this, or you break this degeneracy. One state has needs a lower energy than the other one. That is induced by the fact that the magnetic bias enables essentially electron circulation in a direction preferentially. This splitting that is at the basis of Faraday rotation and non-reciprocal response is proportional to the amount of magnetic bias you apply. So a good magneto-optic material gives you a bigger split. Typically these effects are weak, so you need large magnetic bias to get enough splitting. Can we do the same applying a different quantity that is odd under time reversal? What we suggested is that completely classically you can get the same effect by actually applying an angular momentum to a cavity. So we started from a circularly symmetric cavity, a hollow cavity, and we started moving a medium in the cavity. In this case, there is no electron motion. It's simply a classical problem. But what happens is that the originally degenerate modes of this cavity, the fundamental modes, right-handed, left-handed, they have the same frequency of resonance. They actually split because one mode fills a longer cavity than the other one because of Doppler shift. So one resonance frequency is smaller than the other one. And that is equivalent to Zeeman splitting. This split is again proportional to the applied angular momentum, but it's easier, arguably, in many instances, to apply an angular momentum than to apply magnetic bias. You don't need magnetic materials, essentially. So this one is a simulation to show you how the system works. It's a three-port device. It's a power divider, essentially. You have a resonator in between. At the resonance frequency, power splits evenly between the two ports. In fact, 4/9, 4/9 on the two ports. 1/9 gets reflected because of passivity. But what's interesting is what happens when you start spinning a fluid or a medium in the cavity. And this is done for sound, for acoustic waves. So when you start spinning the fluid, the wave from port 1 actually couples all into port 2. You notice that the standing wave at the resonator is actually excited asymmetrically. This is due to the rotation of the fluid. And you can align one of the two zeros to one of the ports, and that is what gives you isolation. But this asymmetric excitation is a function of the spin. It's not a function of the signal. So when you come in from port 2, the zero will be aligned to port 1. That's what you see here. And therefore, everything goes to port 3. And to port 3, from port 3, it goes to port 1. So this builds the functionality of a circulator for acoustic waves. Actually, magnetoacoustic effects are very weak. So it's interesting that you can build a circulator for sound without magnets and with a quite simple, actually, setup. What is particularly surprising is the velocity that is required to get isolation. In fact, in this example, this is infinite isolation. It's a full zero node on this thing and on this part. And this comes with a velocity of the medium that is 500 times slower than velocity of sound. So there is a large contrast between the two velocities. You can prove from couple mode theory that this actually is a response associated with the quality factor of your cavity. In fact, you can prove that the optimal velocity that aligns the node to one of the parts is divided by the velocity of sound is inversely proportional to the Q factor of your cavity. And this is actually a realization. It's 3 fans inside the hollow aluminum cavity. When the fans are off, of course, the system is reciprocal. When you turn on the fans, you measure this large isolation. You can, this is kind of a tabletop experiment. It's with airborne sound, so you can actually listen to this, and you get 40 dB isolation from port 1 to 2, and this is a symmetric device. So we are in the business of metamaterials. How do we translate this into a material? These structures are actually sub-wavelength compared to the frequency of interest. Can we build a material out of this? So imagine that we connect these circulators made with a spinning fluid in an hexagonal lattice like this. And let's see what happens at the frequency in which this structure provides isolation. So I excite the structure somewhere in the lattice, and if you trace this sound, you will find that actually this stays trapped in this corner. It will not get out because each of these is isolating and doesn't transmit to the other part. However, if I excite this structure at the edge, so for instance here, I will see this the sound flows here, hits the edge, would be reflected at the part, but since this is a circulator, has to bounce this way. And then from this other edge bounces here, and so on, and it will propagate along the edge. Notice that this chain of circulators would not allow back reflections, it's one way, and would not allow propagation in the bulk. In fact, if I remove one of these circulators from the edge, sound will find its own path on the new edge to replicate this phenomenon. So you have just one-way propagation on the edge. What's interesting is that this phenomenon, this transport of signals, is very much equivalent to what happens in the field of condensed matter physics for topological insulators. Topological insulators is a hot topic in physics, and these are materials that are insulating in the bulk, like what you see here. The signal cannot propagate in the bulk, but they conduct on the edge, and they conduct only one way. In fact, the propagation on the edge is protected by symmetry. In the same way, the spin of these structures, it's a bias for the metamaterial that you see here that enables this strong protection. This picture shows you the typical topological shapes. The reason why these are called topological insulators, I think I have a slide here. This is the field of electronic topological insulators, in which the specific topology of the energy bands is the one that determines the nature of the edge modes that exist in the band gap between valence and conduction band. The topology of these two bands will determine the existence of these edge modes that are symmetry protected, and they are very robust to disorder, because since these are supported by the topology, it's very difficult to change the topological invariant of the surfaces of these two bands to change the nature of or the number of these topological states. Basically, what I'm suggesting is that this lattice of resonators with this bias translates these concepts from electronics to photonics or phononics. Now I showed you for sound, I will show you in a moment for light, by applying this strange form of bias. This is actually a nature of the topology, the band structure of this acoustic metamaterial, in which you see without spin, you get this Dirac point here associated with the hexagonal lattice. These are the band diagram of the modes propagating in the lattice, in the acoustic lattice. And as you turn on the fence, you open this gap, and this band gap has the topological order, non-trivial order. Therefore, you can prove it here looking, this is the Berry curvature. This essentially shows the topology of the two bands that indeed guarantees the presence of these edge modes at the edge of the structure. And you, by turning on the velocity to these values, you can actually open the band gap and ensure a continuous bandwidth over which you have this topological propagation. These are examples of structures that indeed support this phenomenon. This is a strip of metamaterials in which in the band gap you notice how we find indeed these one-way edge modes localized at the edge that propagate in this direction back and forth, and over the whole band gap they provide one-way signal transport that is very robust, that doesn't change if you apply disorder. An example of this is if you start truncating the edge in different ways. It doesn't matter how you break the edge, the signal just travels one way, is not scattered into the bulk, and doesn't reflect back. Or you can think of realizing domain walls for these structures by spinning with different circulation two sides of this lattice, and you create these reconfigurable one-way waveguides over a full band gap of the structure. Now, can we translate this nonreciprocity into electromagnetics? So that's a bit more complicated because speed of light is much faster than speed of sound. The way to do it is to start from a symmetric, circularly symmetric ring that supports degenerate modes, and then apply a periodic grading to it that essentially splits the modes, and this distance is proportional to the amplitude of modulation of this grading. Of course, this is still completely reciprocal because you're not breaking time reversal symmetry, so the modes are still degenerate. But then when you start modulating in time each segment of this grading, you can make it look like it's moving. And what's interesting is that you can modulate much faster than what you can mechanically move in a circuit or in a photonic material. So you see here that indeed we now preferentially pick a different polarization, a different handedness for the two frequencies, and that is equivalent to Zeeman splitting, and you can use it to build a circulator or an isolator. So using, for instance, this scheme, we proposed this structure here in which we illuminate. So this is a microring resonator that is coupled to two waveguides. It's an add-drop silicon photonic device. You send light from port 1 and this goes through, but when you send it from port 2, because of this modulation, reciprocity is broken and light actually goes to this other port. You create essentially a 4-port circulator out of this modulation. And again, what is nice of this is that you can modulate very slow. We're modulating at gigahertz frequencies, and we excite the system at hundreds of terahertz. This is a 1.5 micron wavelength design, so 200 terahertz. So it's a 5 orders of magnitude difference between modulation frequency and signal frequency, and with a moderate Q factor for silicon photonics and a small modulation amplitudes, you can indeed get a nice isolation between parts. At RF, the solutions are even easier to implement because we can rely on varactors. This is a design at a few hundred megahertz in which we use the 3 LC tanks connected together with varactors. They are actually connected through shorts, so they're strongly coupled in this case. And by modulating these varactors with the same modulation frequency but different phases, you can make this circuit look like it's rotating slowly. And then when a signal comes in at port 1, it will go all at port 2, and then from port 2 to port 3, and from 3 to 1. So in a small compact device that doesn't have any material that is not already in an integrated circuit, you can realize a circulator that you can use for a kind of integrated circuit or like RF printed circuit boards. Notice also the size of this device. It is very small compared to the wavelength because it doesn't require magnets or big structures. Again, also this system, you can put it in lattice and it creates the same type of protection. Topological order, you can create cavities that resonate only one way. This supports only one-way mode, or robust edge propagation independent of the truncation. And as another way of showing the topological robustness of this system, this is a simulation for an ideal structure that is simulated that is modulated uniformly throughout the array, as in our theory, and you see indeed this protection. But then when you add noise to the modulation scheme, the field that you induce in the lattice is essentially the same. There is no difference, because to avoid the presence of a topological mode, you need to change the topology of the bands, and that doesn't happen through continuous changes. It happens only through drastic modifications of the array. So noise typically doesn't affect much unless you go to extreme values. It's the same reason why it's difficult to, it's impossible actually to continuously transform a sphere into a donut, or one topological order to another. Here, as long as we continuously change the modulation scheme, the topology of the two bands is not affected, and therefore the topological mode exists. So in these examples, I showed you systems that are non-reciprocal for guided waves. Another interesting opportunity is offered by systems that actually are non-reciprocal for free space radiation. And there are two examples of technology in which we face challenges because of reciprocity. One example is energy harvesting, and another one is antenna radiation. So if I build a very good absorber to get energy from a source, like a thermophotovoltaic source, reciprocity, Kirchhoff's law, tells me that this good absorber is also a good emitter because of time reversal symmetry. In the same way, if you are in the field of antennas in electromagnetics, you know that when you measure the radiation pattern of an antenna, that's also the receiving pattern of the antenna because of reciprocity. I don't need to measure how the antenna receives, I can just measure how it transmits. And that's not necessarily a good thing if I want to avoid listening to echoes that come from my radiations or being jammed by incoming waves. So we've been exploring ways of using, again, time modulation and mechanical motion to build non-reciprocal systems that can absorb without emitting, thermally emit, or that can receive without transmitting, or vice versa. An example of that is this simple system. It's a leaky wave antenna. This is a conventional type of antenna in which you take a waveguide, an open waveguide, and you apply a regular periodicity such that you bend the band diagram inside the light cone so that for certain frequency you get directive radiation at a certain angle. You notice this band diagram is symmetric, as it should be because of reciprocity. But when you start modulating in time, this is modulated with a linear momentum. So the antenna looks like it's moving in time, like a tapis roulant, like a moving platform, slowly, but it's sufficient to actually change the band diagram into this one. You notice this mixing of frequencies that come from the mixing between modulation and signal. But what's important is that this mixing is asymmetric. So you can create very strong interband transitions on one side of the light cone and much weaker on the other side. And that translates into an antenna like this one, in which simply there are, as I said, a leaky wave antenna in which the defects, the periodic defects are loaded with varactors that respond to the input signal, and then we excite the structure with a combination of our radio signal and the lower frequency modulation signal, just a tone that breaks reciprocity. And when we measure the structure, in absence of that modulation tone, you get a symmetric pattern within the experimental capabilities that we have at UT. But when we introduce the tone, then we see a very large difference between this directive pattern in transmission and no reception. So the two patterns are completely distinct. And in particular, in this example, we decided to push the receiving pattern below the light cone so you don't get any reception. So this is an antenna that combines an isolator in the structure itself. I was telling you that another way to break reciprocity is to break the third assumption of Lorentz reciprocity theorem, that is the linearity of the materials. This is particularly interesting because it provides a venue to break symmetry without an external bias. What I showed you so far doesn't use magnetic bias, but uses some form of bias that is, in this case, an externally applied time modulation of mechanical motion. Can I use the signal itself to bias my material? To do that, I need nonlinearities. And in fact, there has been some work in recent years using third-order nonlinearities to do exactly this, to create a structure that from one side transmits, from the other one reflects, based on nonlinear materials. A simple way to understand how such a nonlinear isolator works is to assume that I have a certain structure, I excite it from the left, and I get a notch, like a dip in transmission because of a resonance. Imagine that now this structure is nonlinear. So when I increase the intensity, that dip actually shifts in frequency. And you can write this frequency shift easily as the overlap integral between the intensity distribution in this volume and the nonlinearity coefficient. Right? So the amount of change in permittivity in index of this in this volume corresponds to a frequency shift. The larger I pump, the more this shift is. And that makes sense. However, if I now build this structure to be asymmetric, when I come in from the other side, I may get a different frequency shift, for instance, a larger one. And now I have two frequencies for which I isolate, for which from one side I transmit, from the other one I don't. The degree in which I can do that is the asymmetry. The important factor is this one, is the asymmetry coefficient. How much is the contrast between the field that I excite when that I induce when I excite from the left and the right, this kappa coefficient. However, if you look at the performance, the metrics of these nonlinear isolators proposed so far in the literature, they are quite poor. They either show very small isolation performance or they show very poor transmission. So we got curious, what's wrong with these devices? Why it looks like there is some trade-off that people are playing with in this context. And we have found actually what is the problem. It's actually very simple to realize what the problem is. Consider the excitation of these structures for low intensities in the linear regime. And in this case, time reversal symmetry applies. So when you excite from right or left, you induce different fields, but transmission is the same. And the reflection is also the same if you assume that there is no loss, or at least the amplitude. The phase may be different, but you can choose a different reference plane and make it the same. By the way, this theorem that I'm showing you applies also to lossy systems, introducing another part essentially, but it makes it more confusing. So I prefer to stick with lossless structures and show you indeed what is the trade-off that I'm talking about. So if you apply a time reversal operation to this cavity here, you get this. So now what you see is that all the waves have flipped because I'm reversing time, and the fields that I induce are actually the conjugate. You can prove from Maxwell's equations that's what the reversal operation does. Now this system is linear, so superposition should apply here. And what it means is that the field that I induce here, E left conjugate, has to be the sum of this coefficient times E left plus this coefficient times E right. So this always holds for any point in that volume. This is an arbitrary volume actually. This works for arbitrary systems. Then you apply this inequality here and you derive a simple relation between the asymmetry coefficient and the reflection at the port. Interestingly, you can't have an electromagnetically asymmetric structure if the reflection coefficient is 0. If the reflection coefficient is 0, these two sides tend to 1, so the structure has to be symmetric electromagnetically, even if geometrically it's very asymmetric. Or in other words, the transmission coefficient from both sides is bound by the degree of asymmetry. So to build a nonlinear isolator, I want a very nonlinear structure, a very asymmetric structure. I cannot do it unless I pay a price of low transmission. This is a numerical example to show you how this works in practice. I mean, it's a pictorial example. So this is an asymmetric cavity. I excite it from two different sides. I have some reflection at the two parts, and I have different field distributions. So this is a good structure to build an isolator, right? I can put my nonlinearity here, for instance, where I have a 0 there and the maximum here, and I get a very different response from the two sides. However, this structure has reflection. How do I remove reflection? I can match it. I can add the system here, and now there is no reflection. However, you look at the field distribution, it's the same everywhere. Now, wherever I put nonlinearities, I get the same response from the two sides. I get the same transmission, actually. There is no isolation possible. And indeed, if you monitor the fields at every point and take the ratio of field intensities when you excite from the right and the left, you see that you are always within the bounds. In fact, these simulations show that the bound is tight. It always, you can always find a point that reaches the bound. So essentially, there is a trade-off in this nonlinear isolator between the asymmetry in transmission and the level of total transmission. If I bring it down, these two curves can open up. These are optimal structures designed to reach the bound, but you can't do better than this as long as you stick with a single resonator. Because when you go from the linear regime to the nonlinear case, this theorem still holds as long as it's a single resonator involved in the system. When you instead use two nonlinear resonators together and you properly shape the response versus intensity, this transmission versus intensity for two resonators, both nonlinear and separated by a proper delay line, what you can do is to realize a structure that allows, there is a solution that obeys time reversal symmetry for which from port 1 to 2 and from 2 to 1 it allows total transmission, but there is a second solution, this is a bistable problem, for which you have a 0. In this case, you can actually isolate fully with full transmission from the other side within a range of intensities. And these are optimal charts that tell you what is the phase delay you need to introduce to get the maximum possible range of intensities over which you get a large nonlinear response, non-reciprocal response, and still also full transmission. This is an example of how this would work. These are two metasurfaces, both with multi-quantum well nonlinearities, that are designed to have these two different dispersion with intensity. And if you excite them with a temporal excitation like this blue signal, from one side you get full reflection, so transmission is 0. From the other side, you get full transmission. So you can do this large asymmetry over a large range of intensities, actually. This structure is a good nonlinear isolator. This one is actually an experiment that shows how you can actually build this. This is a nonlinear isolator, so it's a passive device that is based on two nonlinear resonators back to back. And when you excite it from opposite sides, you indeed transmit from one side and reflect from the other one, and you can isolate. Also, in this case, you can use this as a building block to build a topological insulator. So now this one is a self-induced topological order. It's induced by the signal itself. So in this case, it's a linear array. It's a 1D problem. In the low intensity regime, this supports a regular band gap without much, with a trivial topological order. But when you increase the intensity, you see that the band gap closes, and then when it reopens, it becomes non-trivial. It acquires a topological order, and it supports an edge mode. And you can see this in this other experiment, in which we put together an array of these elements with back-to-back varactors. And then we monitor the input admittance of the structure. The blue line is the measurement for the array itself. You see several bulk modes excited in the structure. And then the other lines that you see here are different measurements done by shorting different portions of the array. So this defect, this defect, this defect, so on. When you do the same measurements with the high intensity excitation, you find always this edge mode that is robust to disorder in the array. So this realizes a structure that self-reconfigures, that transmits the signal through, but it finds its way around the defect by playing with the topological order of the band gap of the array itself. Now, I switch a little bit gear because I was telling you about the bounds that passivity gives in metamaterials. And to introduce this last topic, I want to talk about this holy grail of metamaterials, that is cloaking or invisibility. Right? This is a topic that I was actually working on when I was in I was working in Pennsylvania when I was with Victor too. So the question is, can I make this object invisible or non-scattering? The scattering of an object is related to the mismatch in boundary conditions between the background and the object itself. And the idea at that time was, can we build a passive material that scatters light with a different phase, such that the two waves interfere destructively and cancel each other, so that the final result is actually full transmission, because there is no scattering, no power diffused around the object. You can indeed do that. This is an example of a demonstration of this. These are blocks of metal that are put in different configurations in front of the antenna, and here you see some cloaked structures in which we build these layers around to make them transparent to the impinging frequency, and indeed you see the difference. These are measured fields. In absence of the cloak, you don't transmit much. Actually, this is the reflection coefficient is mostly blocked by the rods, but when you apply the cloak, this is the comparison between the cloaked case and the case in which there is nothing in front of the horn. Essentially, it restores the same radiation patterns. You can do this for different orientations of the rods, different configurations. Around the frequency for which this is cloaked, you always get full transmission through the structure and over a relatively good bandwidth. And in fact, we have explored optimal designs for radio-transparent antennas that can transmit and receive, but yet do not scatter, or scatter much less than the bare antenna. Now, the problem with these structures is that any metamaterial scheme that relies on passive structures is fundamentally limited in the bandwidth over which this can be achieved as a function of the scattering reduction. There is a bound, it's derived in this paper here, between the scattering reduction and bandwidth, and all available cloaking schemes fall within this bound here. There is this region here, it's not accessible with linear passive materials, but if you use active cloaks, then you can get out of this system, and that's what we've been exploring. In fact, in this direction, an interesting opportunity is offered actually by the field of what is known as parity time symmetry. The systems that are symmetric after an inversion of space and time, inversion of space and time at the same time in these structures. So an example of that is if you ask yourself, what is the surface impedance required to suppress the scattering from a circular cylinder? You can do the math and find that in the limit in which the surface is close to the cylinder, you get this interesting constraint on the required impedance. On one side of the structure, the impedance should have a positive resistance. On the other side, should have the inverse of that resistance, should be active, essentially, have a negative resistance. And indeed, if you look at simulations, this is the case in which you have only the passive side, and this is the case in which you have also an active side on the opposite side. The combination of this passive-active configuration, one time reverse of the other, allows full transmission and recovery of the signal without shadows on the backside of the object. You can make this system stable. This is an excitation. In the transient, of course, there is scattering, but at steady state, this will recover its shape, and it's fully stable also when you excite it from the active side. And as an experimental realization, this was a 1D experiment in acoustics that we did by loading two loudspeakers with circuits that are time reversed of each other, one passive, one active. And indeed, this is the experiment. You can see that when you excite from one side, you have full transmission, and interestingly, you also have large absorption at one of the two sides. At the passive side, this system is actually absorbing largely, and that's because the active side compensates for whatever signal you dump into the passive system. The last thing that I want to briefly show you is that, interestingly, this system realizes in a simple and practical way the idea of negative refraction, of what I showed you at the beginning as one other holy grail of metamaterials. The idea is that if I now start putting apart, introduce distance between the passive and active side of this 1D transparent system, I find that the active side has to send back a signal, a replica of the impinging signal to the passive side with an increased phase advance. And that phase advance corresponds to a negative phase that the system acquires when it transmits the signal. In practice, this is actually what you would see if you illuminate the structure. This is a passive array of these elements, and this is an active array of time reversed of the same elements. When you excite it from the left, you get this effect of negative refraction that comes from the fact that the active array is illuminating, sending a replica of the signal with a phase advance back to the active side. And that indeed realizes the equivalent of a negative index planar lens, so you can actually image details of a structure on the opposite side by exploiting these two surfaces, one active and one passive. Yeah. So this concludes my talk. Essentially, there are a few opportunities for metamaterials engaging large nonlinearities, nonreciprocity, mechanical motion and time modulation, and gain to push the technology of metamaterials forward with interesting opportunities for technology. Thank you.
We have time just for one or two quick questions. I know there is a class coming in, so one quick question. Yuri.
Yes. Correct. It's not constant, but it changes with a certain pattern, right? Angular pattern. Yes. Correct. Correct. Yes, so you need to... The feedback, actually that's a very good question. So the feedback comes from the scattering itself, right? So you have to tailor the gain and the loss in the system to follow the shape of your structure. And the feedback will come from the scattering that happens in the transient. You have to make sure that this feedback builds up so that in steady state you get the full transmission through the system and no scattering. So it will reach steady state. I can tell you more about this. Thank you.
All right. We don't have any more time. If you have any questions, Andrea is going to stick around.
I will be here.
So one more time, let's thank Andrea again.